We're back. And before we talk about reactions, again, I'm going to have to give you more foundation, more fundamental building blocks to build upon. And that way you can go into these reactions with a little better sense or a little bit smarter as how you approach them at least. Okay? So one of the first things that I want to talk about in this lecture video is this concept of delocalization again. All right, I'm just going to briefly introduce it one more time just to say, hey, you remember this term? Because this term could come back, and that means electrons can actually move throughout the molecule. That's all that I want to say about it right now, okay? So we saw this very early on in lecture 1 when we started drawing Lewis dot structures and so forth. And it's going to come back in this lecture as well a little bit later on when we talk about more complicated molecules and how to react with them. Because delocalization could take part into the decision about the product that's going to be formed in those reactions. So I just want you to keep in mind electrons can move throughout the molecule. And the way that this will relate to reactions when we get to that point is carbocations will also be affected for that reason. So as you can imagine, if electrons move through the molecule, those are negatives that move through the molecule, and if those negatives and those positives are both there, then they can start affecting each other, and that's exactly what happens in the reactions that we're going to start seeing. So delocalization is there. It never goes away. It happens in certain molecules, and these are the ones that we have to pay attention to. So just kind of a quick hint, or a quick little nudge, that's what we're going to be seeing later on in these reactions that we're going to be doing as examples. So another term that we need to discuss is something called regioselective. All right, so that's a fancy term, isn't it? Regio, R-E-G-I-O, selective, and hopefully you'll know how to spell selective. Regioselectivity or regioselective compounds and reactions. What this basically means is that it's going to go back to tertiary, secondary, and primary. So we already know the stability order of those carbocations when they form. So tertiary, secondary, primary carbocations. Tertiary is more stable than secondary. Secondary is more stable than primary. All right, so this priority ranking is going to be pretty important, because this is going to determine if the product that is formed is a single product, which means only one, or is going to be a mixture of various products, which of course means more than one. Well, regioselective is a word that we use to describe this concept. So if it is a single product, only one product can actually form, that of course is going to be way different than if there's a mixture of products that could be formed. If there is a mixture of products that are formed, this is not regioselective. And you need to keep in mind the last part of this word, selective. So a mixture basically means the reaction is not being selective on the products that are getting formed. Anything is fair game. If it's want to form, it can form, so be it, whatever. The reaction doesn't care. But regioselective, if it is highly regioselective, then that means only one product is formed out of all of the choices that could be there. And all of this is really tied to tertiary, secondary, and primary. So this is something that we're going to be bringing up throughout these reaction examples. I'm going to be talking about regioselectivity. I'm going to be talking about the various different products that could form from these reactions. And sometimes we don't call it regioselective, but sometimes we refer to it as the major product and the minor product. So when we do talk about major and minors, we are acknowledging that all of those products could exist at some point in time. However, the reaction could prefer one over the other, and that's why we call one the major, because that's the preferred one, and one the minor, or maybe multiple minors that could be forming from these reactions that we're going to be seeing. All right, so it's just a term. I want to throw that term out there now so that way when I use it and begin to use it in these reactions, you're not thrown for a loop and wondering what on earth that what that word means, and you'll know the definition of it. All right. Something else is that out of these products, when we do get these major and minor products and we begin to have choices, these choices are going to be called constitutional isomers. All right, so what does that mean? Okay, well, let's kind of give you an example, and maybe you'll see that a little bit better. Let's say that I have a double bond that's here, and on this carbon, I have a CH3 group and a hydrogen, and then over here, I've got maybe a CH2, CH3 group, and here I've got a CH3 as well. All right, so let's say that we react this compound with HCl. Okay, so at this point, I at least know this. I can redraw the molecule just like it is, okay? And then I'm going to erase the double bond, and I'm going to open up two sites of attachment. One's going to go here, and one can go there, and H could go there, and Cl could go there, right? Okay, so there's one type of product. There's one type of product right there. Is it the major one? Is it the minor one? Is it the only one? Well, that we can't really answer yet, but we will get to that point. However, you could have had a choice, all right? And that choice could have been this. You chose to put the hydrogen on the left-hand side. Well, someone else could have chose to put the hydrogen here on the right-hand side, and that forces the chlorine up here to the right to go to the left-hand side. So we just flipped them. That's all that we did. And this is a fair kind of moment as well. So is this the major product, or is this the minor product, or is this the only product? That we just simply don't know. We don't know yet. We will be able to determine this later on toward the end of this lecture module, but as of right now, this is a question that we're going to have to put a big question mark beside of and say, we'll come back to this. We'll talk about this. We'll get this. Not a problem. Well, these two things are called constitutional isomers. All right, the reason they're called constitutional isomers is because they're made up of the same numbers of everything. Same number of carbons, same number of hydrogens, same number of chlorines in this case. But they are drawn in a different way. They're hooked up in a different way. So if you were looking at longest carbon chains, all right, 1, 2, 3, 4, and 5. Here is the longest carbon chain that we have. And in this example, that chlorine is on spot number 3. And methyl group is on spot number 3. All right, down here at the bottom, we still have a 5-carbon long chain. 1, 2, 3, 4, and 5, right? So here we go. However, this chlorine is now going to be on carbon number 2 because we number closest to the left-hand side. Chlorine gets priority because it's slightly different. We don't see it that often compared to a methyl group or an ethyl group. So that's going to get spot 2, and methyl gets spot 3. I numbered them differently, didn't I? Right? This is spot 2 carbon, this is a spot 3 carbon, and in this case, I have a 2 chloro and a 3 methyl group. Up here at the top, I number closest to the right-hand side because that's where both of these groups are going to be. This is spot number 3 for each one of those. So this is going to be 3 chloro, 3 methyl. Well, because they are numbered in a different way, it's the same number of carbons, same number of chlorines, same number of hydrogens. They are just hooked up differently, and we call that a constitutional isomer. So these products that we're going to be getting from these reactions, the major products, the minor products, if we do have a mixture, those mixtures are going to be regarded almost every single time as constitutional isomers. It is basically the same molecule, it's just things are hooked on it in a different order. And that is the only difference that we begin to see here with these reactions and with these products. Another concept that I want to bring out and lay it out on the table for you is something that's going to be called Markovnikov. Oh, whoa, that sounds fancy, doesn't it? Well, let's spell it. It's harder to spell than it is to say sometimes. Markovnikov, Markovnikov. I like to call this Marky Mark. I kind of an 80s kid, and growing up in the 80s, you probably were aware of Marky Mark. And if you don't know who Marky Mark is, then maybe you need to type in a Google search really quick to see who Marky Mark was, because you'll know that person by probably a different name in today's generation. But Markovnikov has a rule. Marky Mark's rule is what I call this. And Markovnikov rule states this. I'm going to be all textbook here for a minute. All right, so hydrogen. In the world of alkene reactions, hydrogen adds to the sp2 carbon that is bonded to the greatest number of hydrogens. That's what the textbook gives you. Does it make sense to you? It might, and if so, good. But you might read this and say, what on earth? What is that book trying to tell me? I mean, that makes no sense. So, layman's terms, people. That's what we're doing. Layman's terms. I need to have a discussion with you. If I want you to be textbook pros, I would just say, go read the textbook, and it will save me all the time and trouble of recording these videos. I mean, my job would be so much easier if that's just what I told you to do, but who wants to do that? You're paying for a service. You're paying tuition money for a reason, and that's for me to at least try to explain to you the wonderful world of organic chemistry, right? So here's a moment where the textbook says this, right? Hydrogen adds to the sp2 carbon that is bonded to the greatest number of hydrogens. All right, so here's Tracy's term. Tracy's term is H plays with other H's. That's what that basically is saying. Isn't that a little bit better? But think about hydrogen. If I put it in that term, you know, it might flash back to high school for you. Maybe, right? H's play with only other H's. It's like the jocks. The jocks only kind of hung out with the jocks. The book smart people only hung out with the book smart people. You know, the primpy little preppy girls and guys would only hang out with them. You had your cliques. That's what you had. We've all been there, and you probably have seen the movie Breakfast Club. If you've not, then you need to go watch the movie Breakfast Club because you're missing out on a wonderful, great movie. That's when movies were good. So hydrogens play with other hydrogens. Okay, I can get that. I can maybe understand that a little bit better. They're cliquey. That's what they mean. So an sp2 carbon is just a carbon that is double bonded to another carbon. So what this is basically saying is that Markovnikov's rule will follow almost, I'm going to key that right there, almost every time. And if it does, what this means is that hydrogens will come into the picture. And a general rule that we want to follow is that that hydrogen will look at the molecule and it will go to the carbon in the double bond that has the most hydrogens. Sometimes they will be the same. If they are the same, then there's no choice, there's no preference. Hydrogen's just going to go to both of them. One time he'll go to the one on the left, another time he'll go to the one on the right, and we get a mixture of different products maybe because of that. I don't know. We might see that. But that is what Markovnikov's rule is basically saying. Not everything will follow Markovnikov's rule. That's very important. We're going to actually see at least one of these types of reactions in this lecture series. And we call that anti-Markovnikov. Anti-Markovnikov means the hydrogens don't play with other hydrogens. We get a little fluke. And that hydrogen comes in and says, ew, I don't want anything to do with those hydrogens, and it goes on to the other carbon instead. That is anti-Markovnikov. or anti-Marky-Mark. So whenever I say Marky-Mark in the future, whenever I say anti-Marky-Mark or anti-Markovnikov, this is what we're referring to. We're talking about the actions and the actions of the hydrogens in specific. Okay? Or specifically in specific. That didn't make any sense. Of course, a lot of things that I talk about don't make any sense, do they? Okay, so anti-Markovnikov we now have on the table. Delocalization we know is going to play a role here. Regioselectivity we also know is going to play a role. All of that is very, very important. All right, so if we look at an example, here we see this. In this example, the reagent over to the side, they've named it for you. They did just some hard work. 2-methylpropane. All right, 1, 2, 3. There's my 3-carbon chain. On the first carbon, I have the ene, so propane. And then on the second carbon, I have the methyl group, so 2-methylpropane. And we're going to react this with hydrochloric acid. And when we do this, H goes on to one side, Cl goes onto the other. All right, so H could come around and connect here first. And then that will open this side of attachment up, and that's where chlorine is going to go. If this is the way that that happens, then this is the product that we're going to be forming, right? You see the chlorine there toward the end, and the hydrogen more to the center. All right, well, we don't have to do that. That's not our only choice, because the other choice would have been, well, hey, what if, right? What if the hydrogens went here and went there first? That would have opened up this carbon for the free side of attachment. And then second step, that's where chlorine's going to go. So chlorine will end up here in the center, and then this is going to be route number 2. So we also have that structure as well. Both of these structures could form, maybe. We just don't know that yet. All right. But the question says which products of these would be more preferred over the other. If both of them could form, is this really regioselective? Which means, does it prefer one over the other? And the answer is yes. It's going to prefer one over the other. Because let's talk about Markovnikov's rule first. Markovnikov's rule says hydrogens plays with other hydrogens. So if it comes in here and this double bond breaks, right, and it turns into a single, and we get 2 sites of attachment that open up right there, where's that hydrogen going to go? Well, it looks at this carbon to the left and it says, ew, you don't have any hydrogens. I don't want anything to do with you. You're not part of my clique. And this hydrogen sees the carbon to the right and it says, hey, you've got 2 already and I feel more comfortable in this crowd. So I'm just going to move my way on in because we've got so much in common. Yay! Right? I mean, that's the concept there. So hydrogen is going to go here, and we would form not a CH2 now, but a CH3. And there takes up that bond. Well, the carbon to the left now has this free bond, and that free bond, well, it needs something there. That carbon's not going to stay around. Look at this. This has formed a carbocation momentarily. What type of carbocation has it formed? Tertiary. How do I know that? Because that carbon is attached to the one on the left and one on top and one to the right. So that tertiary carbocation is going to be kind of stable, but look at what we just did. Markovnikov, Marky-Mark's rule, told us where the hydrogens went. When we used Markovnikov's rule, what we did in a backdoor approach was help determine the most stable carbocation that could form in that reaction. So if we put the hydrogen to the left-hand carbon, the carbocation would have formed here to the right-hand side. That's a primary carbocation, isn't it? And we've already talked about the difference between the stability of a primary and, in this case, a tertiary carbocation. Out of the 2 choices, the primary is not stable. The tertiary is more stable, and the molecule is going to arrange itself to make it more stable, even if it's temporary. Even if it's temporary, it prefers the more stable location. So Markovnikov basically allows us to look at this hydrogen, if that's what gets added on first, to look at the hydrogen and say, slap, you're going to go there. And in this case, to the right-hand side. This forms a carbocation. By default, this is the most stable carbocation out of those two choices that I have presented to you in this example. When that carbocation gets formed, this negative chlorine is, of course, going to go onto that carbocation, and that's what you're going to see here. So therefore, the tert butyl chloride is going to be the most stable product out of those two choices that we've been presented with. It's all because Markovnikov rule was followed, a more stable carbocation was generated. Okay? So that's how we're going to answer some of these questions. If they do give us choices, and they take some of the work away from us, and they say, listen, here's your products. You're going to have to tell me which one's better than the other one. This is the way that we do it. We look at our choices. We look at the hydrogen movement, take in Markovnikov's theory, and then we're going to take a look at the stability of the carbocations. All right, here's another case. It's basically the same as what we saw before. It just kind of lays it out all on the table for you. So it gives you the middle steps. It gives you these kind of transition states that we begin to talk about. So if you look, here they give you two routes. The first route that they have illustrated for you is the formation of the tertiary carbocation, and this allowed Mark to take place. All right, so Markey's rule followed here, and that allowed chlorine to go on to that center carbon. Down here toward the bottom, if you go this route, the hydrogen does not follow Markovnikov, and that forces the carbocation to be on a primary carbocation, and that's where the chlorine would go. But because this is primary, this route is not preferred, and that's why they put an X on it. So out of these two, there is a slight chance. Now, I know it says not formed, all right? But there is a slight chance that I might get very small amounts of that product. You need to keep that in mind, okay? These things are not so clear-cut the way that we want to present them in a textbook. So there is a slight, little bitty tiny chance that I do get this. But out of these two, this one is going to be preferred over the other one. Much more so, okay? Now, is this regioselective? And the answer is yes. This is regioselective because remember, regioselectivity means that the reaction was selective, and it is selective here. We are selectively choosing the tertiary carbocation to give us the product because that is a more stable carbocation. So this is a regioselective reaction that we have. Now, I know I just said that we get both, but that second one is going to be in really, really, really tiny amounts, and that's not really what we're talking about with regioselectivity. Okay, if a reaction was not regioselective, I mean, this would be like a 50-50 mix, okay? Or it could be a 60-40 mix. You get my drift? Large percentages of both or all of the choices that we would have at the end of this mechanism. That is what we call non-regioselective. But in this case, we do have a regioselective reaction. One is greatly preferred over the other, and because of that, that one is going to be chosen over the other one, which means the reaction is selective at that point. All right? Here's another example. Same kind of concept, right? So here we have one propene, and one propene has a double bond, and this bond is going to break, and we're going to open up a side of attachment here and one there. So in the top route, we have the addition of hydrochloric acid. So H goes on one side and CO goes on to the other. Well, if we follow this with Markovnikov, H goes on first, right? So Markovnikov says hydrogens play with other little hydrogens. Again, that's awful, but that's the way hydrogen is. Well, do I go to the left or do I go to the right? To the left-hand side, it has one hydrogen. To the right-hand side, it has two hydrogens. So hydrogen's going to go here. And that turns this into a CH3 group instead of a CH2 group. So I'm just going to erase that bond down there, and I'm going to clear that up a little bit. All right? So there we go. Well, that frees up a carbocation. That carbocation is right now at this moment in time a secondary carbocation. This carbon's got one to the left and one to the right. So that's where the chlorine is going to go, and that's where you see the product formation here. So there's one choice, right? So the other choice that I could have done is I could have went in and I could have said, okay, double bond's going to break, bond here, bond there. Hydrogen goes in, and let's say I did not take into consideration Markovnikov. Well, normally hydrogen would go to the right-hand side, but now let's make it go to the left-hand side instead. All right, so if we do that, this is a carbon with an extra hydrogen on it now. So this is really a CH2 at this point. So I'll condense that down a little bit. I'll just erase that bond to keep it clean. And then we have the chlorine that comes in next. This is a carbocation at this point. However, this is a primary carbocation. Primary carbocations are not very stable at all, okay? To the point where we put X's on them to say they're just not going to happen. All right, now, even though we say that, keep in mind, we could have extremely, extremely tiny amounts. But in the textbook and just for general discussion, they say no. This is not going to work. It's not going to happen. All right. Now, if this chlorine went on, this chlorine would have went there, and we would have had a product that looked like this: CH2 or CH3, CH2, CH2 with a chlorine that was attached to that end carbon. This product, they're going to say, does not form. Keep in mind, again, extremely, extremely tiny amounts could actually be there. But for the sake of our discussion, we say no. This is not going to form, and we could have actually done it here as well. You actually saw the X that was written here to say, no, that was a primary carbocation. This probably is not going to get formed, and that's why they say not formed, because in general context, it would be very hard for us to detect it because such a small quantity actually exists. So is this regioselective? The answer is yes, it is regioselective. It is selecting one product over the other, one route over the other, and it's all due to Markovnikov's rule, and it's all due to the more stable carbocation that gets formed in this process. Here's more regioselective electrophilic addition reactions, EAR reactions. Remember that, right? So if I look at the first one, I see 2-methyl-2-butene. So 1, 2, that's where the 2-methyl comes in, 2-butene. So that's where my double bond is at. So 2-methyl-2-butene. The double bond breaks. I get a side of attachment here, and I get a side of attachment there. If I add HI, folks, it's the same story. Hydrogens play with other hydrogens. So if I look at these choices, it's not a symmetrical molecule, is it? It's different. The carbon to the left has 1, and the carbon to the right doesn't have any. So hydrogen plays with other hydrogens, and it comes around and it goes, ew, and then it goes over to the left, and it says, that's where I'm going to attach. So the hydrogen goes over here to the left-hand side. This is a CH, but now I'm going to draw it as a CH2. So that just helps me clear that up a little bit. CH3, CH2. And this frees up a carbocation. That carbocation is a tertiary carbocation at this point. Very happy with that. It's the most stable carbocation that can form. One to the left, one to the right, one up above. There's 3 things that are attached there. So the iodine is going to go onto that position, and that's where it's going to attach. And that's why we call this the major product. All right, this is the preferred route over the choices that I have. However, that's not the only choice. Okay, we know that. We've been doing this. This double bond could break. Attachment. Hydrogen could come in and just have a weird day and say, I don't want to hang out with you, hydrogen. We had an argument last night, and my mama told me not to talk to you anymore. So over here to the right-hand side, hydrogen goes there. And then that will allow iodine to come in onto this position and form this product, which is what we're going to call the minor product. Okay, well, why does this happen? Why did they write both? Why didn't they just write an X here? Because when this carbocation was formed, look at this. This is not a primary carbocation, is it? This is a secondary. So this was a tertiary carbocation, and this was a secondary carbocation. When these happen, the secondaries are way more stable than the primaries. And because of that, they do show up in a larger amount, but we still call it a minor product. We'll just be able to see it and detect it a little bit better because there's more of it. In this case, this was a primary carbocation that formed, and that's why they X'd this out. They said, no, this is not going to work. It's not going to form. It's going to have what we're going to call no product formation, to keep it simple. And then here in this example, they did the same thing. Down here with this route, they put a big X on this, and they said, no, 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 you can't do this, because if you look at this carbon, this is a primary carbocation. So such a small amount is going to get formed that we're just not going to even pretend like it exists, right? We're just going to say, nope, sorry, nothing there, no product, move on, go to the next problem. So that is the difference that you're seeing there. Here, the next one down here toward the bottom, this is a ring, 1-methyl cyclohexene. So we start with number 1 right there. It includes my double bond, and it includes that methyl group both. So 1-methyl cyclohexene, and we add HBr. So this double bond is going to break, and we're going to have attachment here and attachment there. So hydrogen's going to come in, and it's going to say, okay, where do I go? Well, wait a minute, there's no hydrogens here. Yeah, there is. Okay, there is. The problem is that they just didn't draw them for you. All right, so let's go through and let's draw them. This carbon has 1 bond up, 1 bond to the left, 2 bonds to the right. This cannot have any more hydrogen. It already has 4 bonds. No more. Sorry, move on to the next. All right, well, this carbon, it's got 2 to the left, it's got 1 down below, so that's a total of 3. So that means that this has to have a hydrogen right there. That is the 4th bond. It's not drawn, but it's understood to be there. We're big boys and big girls now, right? In organic. We know that it's supposed to be there. All right, so this HBr comes in, the double bond breaks, a side of attachment opens up here and it opens up there, and H plays with other H's. So it sees this H over on the right-hand side, and it says, you know what, I think I like you. I'm going to hang out here. So 2 hydrogens go onto that now. Well, because 2 hydrogens go there, we just assume that people know that 2 hydrogens are there, and we just leave it off. All right, well, that opens up a carbocation at this location. That carbocation right now is a tertiary carbocation, which is very stable, and that negative bromine comes into that spot, and that is where it goes. Markovnikov rule helped determine this. Regioselectivity is going to take place. And here I get a compound that we regard as the major product. All right, but it didn't have to happen that way. We've already discussed this. We've already talked about it. This double bond could break into a single. I get a bond here, and I get a bond there. Well, hydrogen, instead of going to the right-hand side, could have went here. That would have formed a carbocation there. That is a secondary carbocation. It's only attached to 2 other carbons. That secondary carbocation, though, can stay around, so we don't cross it out like we did primaries. And that bromine would eventually go on in that position, possibly. Well, that's what we're seeing here as our second choice. However, that is a minor product. And the reason is because it's a secondary carbocation versus a tertiary carbocation that was formed here in the very first example or choice of a product. All right, so that's where I'm going to stop babbling. Okay, so now you're seeing where this goes. And folks, I want you to keep in mind, we've not really done any example problems of reactions yet. We are in the process of determining and predicting the different ways that products could form. That's what we're doing. And we're going to apply these to all of the reactions that's going to be coming our way. Now, the acid reaction we have talked about, but that's the only one. HI, HBr, HCl, those are the ones that they've kind of stuck with. We've not done any more than that. So this template in this model is going to be applied to everything that we will be discussing in this lecture module. So in the next video, we'll do some more examples. We'll walk through some more of these structures and product formation and so forth to determine if these things are regioselective or not, and if they are, how to predict the major and the minor products. So that's what we're going to pick up with. Don't take a break. Come back. You're on a roll. I know that you're enjoying listening to me gabble for 35 minutes. So come back. I'll give you some more.